Okay, so we're talking about our circulations in the north-south plane now, so our three overturning circulation cells. And last time we talked about what drives these things, specifically whether they're thermally direct or thermally indirect circulations. We also talked about what these things mean for the winds near the ground, i.e. in terms of our belts of mean easterly and westerly winds at the ground. Now, on top of all that, these things also have important implications for precipitation, because in parts of these cells, we tend to have upward motion on average, and in parts of these cells, we tend to have downward motion on average. And if you remember back just a couple of screencasts, that upward motion tends to favor the production of clouds and precipitation. On the other hand, downward motion tends to suppress it. So upward motion tends to favor precipitation, that's going to be rainier, and downward motion tends to suppress it, so that's going to be drier. So in terms of our circulation cells then, we might expect that this upward branch of the Hadley cell is going to be a rainier place, because we have upward motion there on average. We might also expect that this branch near 60 degrees, where we've got the ferrule and polar cells coming together, we've got upward motion there too, so we might expect that to be rainier on average. And by contrast, on the downward part of the Hadley cell and ferrule cell, that's going to suppress precipitation, and we expect that to be drier on average. And we've got downward motion at the poles too, and so we expect the poles to be drier on average. Here's what it looks like if you put it on the globe. So in this figure, we've got here on the side view, we've got our overturning circulation cells. We've got our Hadley cell here, ferrule cell going the other way, and then our polar cell here in the Arctic region. And so we have our regions of mean upward motion here associated with the Hadley cell, downward motion on the sinking part of the Hadley cell, upward motion near 60 degrees, downward motion at the poles. And they've indicated places that are rainier places here by putting these clouds in. Now, as you might expect, these things have names associated with them. This region of upward motion near the equator, that guy's called the intertropical convergence zone. Intertropical convergence zone. Or ITCZ, intertropical convergence zone. And where that name comes from is that you actually have two branches of Hadley cell here. You've got your northern hemisphere Hadley cell, and you've got your southern hemisphere Hadley cell. And on both sides, the surface parts of the winds are drifting towards the equator from the north and drifting towards the equator from the south. And so you tend to have convergence into this region here in the middle. We're roughly at the equator. And so it's that the name comes from that convergence. It's the intertropical convergence zone. This region of sinking motion near 30 degrees, that's referred to as the subtropical highs, Subtropical referring to just outside of the tropics. 30 degrees is just outside the tropics. And the reason this is high is because associated with the winds aloft here in the Hadley cell and the winds aloft in the ferrule cell, we tend to have convergence into this region at upper levels. And if you remember, convergence at upper levels brings mass into the air column. And by bringing mass into the air column, you make the air column heavier, and so that tends to increase the pressure at the ground. So on average, you tend to have higher pressure in this region at the ground. This place where we tend to have mean upward motion near 60 degrees or so, that's the polar front. We've seen that name before. That's our boundary between our really cold air mass in the Arctic and our somewhat warmer air mass to the south. It's the polar front. And then finally, this region of descending motion here at the poles, that's the polar high. It's the same kind of thing. At upper levels here, we've got convergence in from the two sides. And by converging in from the two sides, And convergence aloft tends to increase the pressure at the ground. Okay, so now what I'm going to say next is actually outlined on the following slide here, but I'm actually going to talk about it while pointing at the figure. So if you want to take notes on the following slide, you can, but I'm going to point at this figure while I say these things. So here at the equator, roughly at the equator, where we've got the upward motion associated with the Hadley cell, that actually tends to be one of the rainiest places on Earth. In fact, on average, it is the rainiest place on Earth, here in the intertropical convergence zone. Quite a bit of the rainfall that we get on the planet is actually in this region, in this band, associated with the upward branch of the Hadley cell. So that's very rainy. On the other hand, this downward branch near 30 degrees, downward motion tends to suppress precipitation, so we expect that to be dry. And in fact, this is where most of the world's deserts are found, in either north or south 30 degrees. So for instance, in North America, we've got the American Southwest and northern Mexico are both near 30 degrees. Those are very dry regions. The Mojave Desert is in there. In northern Africa, you've got the Sahara. So in the deserts of northern Africa are near 30 degrees. The Middle East, very dry region, near 30 degrees. The Eurasian steppe, the southern part of that is basically a desert extending across Asia. That's around 30 degrees as well. And then in the southern hemisphere, the southern tip of Africa, South Africa is a pretty dry place, again near 30 degrees. And then if we extend it over to Australia, that's where the Australian outback is as well. So most of the deserts of the world are in this subtropical high band where you have downward motion near 30 degrees. Now, around 60 degrees up here, we again have a region of upward motion on average that tends to be wetter than average. But it's worth making a distinction between how the rain falls up in this region compared to how it falls in your intertropical convergence zone. If any of you guys have ever spent time in the tropics in summer, you'll know that pretty much most days it's going to rain. You know, pretty much the way this works is it's sunny in the morning, and then sometime in the afternoon you start to get storms building up, and then it rains a bit. And it's pretty regular. It happens, not every day, but it happens, pretty regularly. By contrast, in the polar front region, most of that precipitation is tied up in our day-to-day churning, our day-to-day weather systems. So our low-pressure systems and high-pressure systems that propagate through. And so as a result, the rainfall is much more irregular. You'll get rain associated with a low-pressure system propagating through for a few days, and then it's clear for a few days with the high system, and so forth and so on. So it's much more irregular kind of rainfall up here, but on average, still, it tends to be a wetter place than other places on the planet. And then finally, up here in the poles, with the downward motion associated with the downward part of the polar cell, that's actually really dry. And the poles are basically deserts. There's very little precipitation that falls there. Now, of course, the poles tend to be snowy and icy, and that's because the precipitation that does fall tends to build up year after year after year. But in any given year, you get very little snowfall at the poles. And again, this is basically what I was just talking about. Now, these signals are robust enough that on most days, or at least a lot of days, if you sort of just look at the Earth from space and squint your eyes a little bit, you can see the patterns. I mean, the patterns are really mean patterns, average patterns. So if you average enough, you see the patterns quite clearly. But on any given day, you can sort of see it as well. So for instance, this figure here, I think this one's from the textbook, although I might have taken it from the NASA website. I'm not sure, I don't remember. But sort of just looking at the globe here, we've got a band of sort of rainy weather right along here, kind of like a belt extending across the planet. And that's your intertropical convergence zone. That's the upward part of the Hadley cell, right in this region here. And then on average, we also have another fairly rainy region up here around 60 degrees. Lots of clouds right up in there. And in between, it tends to be relatively clear. So for instance, all the way over here, it's relatively clear. There's not a whole lot going on. Now, there are things going on, right? On any given day, it's not going to be completely clear. But on average, this band right here tends to be relatively clear, and then you've got more stuff going on down here and more stuff going on up here. So your intertropical convergence zone and your polar front. This shows it also. So again, here the intertropical convergence zone stands out very clearly, right? You've got this band of clouds extending all the way across the Pacific here. So there's your intertropical convergence zone associated with the upward part of the Hadley cell. And then you've got another band of relatively high precipitation up in here, relatively cloudy band, sort of maybe 50 to 60 degrees on this particular day. And that's your polar front, right? That's cloudier than average as well. And then in between, it's relatively clear. So right in this band, right in here, there's not a whole lot going on. Now, another thing that's worth mentioning about this is that these patterns tend to shift north and south with the seasons. Basically, what's going on is here, this intertropical convergence zone, what's driving that is heating from the sun. So basically, this is going to be wherever it's warmest on the planet. So wherever your warmest spot is, wherever the sun hits most directly, that's where you're going to get your intertropical convergence zone. And that's going to vary with the seasons. So in our summer, the sun is hitting most directly in the northern hemisphere. And so the intertropical convergence zone is going to set up in the northern hemisphere, under the point where the sun hits most directly. There's a little bit of a lag, like the seasonal lag thing, so it's not immediately where the sun hits most directly, but it's pretty close to that. So as the position where the sun hits most directly moves northward in our summer, the intertropical convergence zone follows it northward. And similarly, in our winter, when the sun hits more directly in the southern hemisphere, then the intertropical convergence zone is going to follow that into the southern hemisphere, where the sun is hitting more directly. So this band of relatively high precipitation is going to move north and south with the seasons. It's going to be wherever it's warmest. This is actually one of the major contributors to the rainy and dry seasons in the tropics. So in the tropics, you don't really have summer and winter. Instead, what you have is a rainy season and a dry season. And one of the biggest factors that drives this is this motion north and south of the intertropical convergence zone and the associated upward branch of the Hadley cell. So in our summer, when the convergence zone moves into the northern hemisphere, that's going to be the rainy season for the northern hemisphere tropics, for Central America, for the northern hemisphere parts of Africa. On the other hand, when that moves into the southern hemisphere, then it's going to be rainy season in the southern hemisphere. So this guy's going to move north and south, and the rainy season goes along with it. Now, I guess I should probably say that there are other contributors to rainy and dry seasons. For instance, you get monsoon circulations. It's particularly in Asia that's set up. The Indian monsoon is a big contributor to the rainy season there. But it actually is fairly closely related to this as well. So it's all sort of tied together with this motion north and south of the intertropical convergence zone. Okay, so far we've talked about the jet streams in the upper troposphere. We've talked about our north-south circulation cells. But is that the whole story? Is that everything? Well, of course not. So for instance, on top of these jets and circulation cells, we also have a series of semi-permanent high and low pressure systems. And actually, this reminds me, there was one thing that I wanted to mention really quick. I'm going to jump back really quick to one of the other slides, and then we'll come back to this. So just going back a few slides here to this guy. So I had mentioned how most of the deserts of the world are at 30 degrees north and south here, and that's true. But that doesn't mean that every place at 30 degrees north and south is going to be a desert. because if you look up the latitude of Houston, for instance, it's basically 30 degrees north. It sits right on 30 degrees north. But Houston obviously isn't a desert. So what's going on? Well, so you also have local effects, right? This is a global pattern, but you also have local effects that you have to think about. And Houston sitting right on the Gulf, that's going to tend to get a lot of moisture off of the Gulf in particular parts of the year, which is going to tend to give you more precipitation than you would have otherwise. So Houston and the sort of the Gulf Coast in general ends up not being a desert because of that, because there are local effects that are driving it, that are affecting the circulations there and the precipitation. Okay, now back to where we were. Here. Right, so we've got our jets, we've got our north-south circulation cells, but on top of that, we've got a lot of other stuff going on. And so let's continue with the theme of starting with, doing big things first and working our way down to smaller things. So the next biggest thing that you would think about is that we have a bunch of sort of semi-permanent systems that set up, semi-permanent high and low pressure systems that set up, mainly associated with land-sea contrasts, but also associated with mountains as well. I say semi-permanent because these are things that set up in a given season, and then they'll be persistent throughout that season, but they'll change with the season. So in the following, going from summer to winter, all of these patterns will change. So for instance, this is what the semi-permanent high and low pressure systems look like in our winter. And so you can see that there's this big old high pressure that sets up, semi-permanent high pressure over Siberia, called this over Asia, called the Siberian high. There's another one that sets up sort of over Canada. It's called the Canadian high. And what's going on here basically is that in our winter, the continents are cold. So, as we go into the winter season, the continents get very cold, whereas the oceans stay a little bit warmer. It's that specific heat thing that we were talking about before. The temperatures swings in the ocean because it has a higher specific heat. It doesn't get as cold. It doesn't get as warm in the summer. So in the winter, the land tends to be cold. The ocean stays a little bit warmer. And so you get a bunch of cold air that piles up over the continents. And this cold air piling up tends to be heavier on average because it's cold. And when you get this heavy air, that tends to give you higher pressure, right? Cold, dense, heavy air, it's going to weigh more, so it's going to give you a higher pressure. The Siberian high is probably one of the biggest signals that sets up in our winter. It's winter after winter after winter, you get this big old high pressure. In fact, if you remember back to when we talked about the record high pressures on the planet, they were found in the Siberian high in winter. Now, we also do have a couple regions of average low pressure that set up in our winter, sort of in the Iceland region here. It's called the Icelandic low, just east of Greenland and sort of just east of Asia as well. And these guys tend to be associated with storms coming off of the continents. They tend to follow tracks that push them off to the northeast. And so you get a lot of these low pressure systems, a lot of these storms sort of tracking off over Iceland. And so on average, it tends to give you lower pressure there. Now, one thing that you'll also note from this figure is that the patterns are much more regular in the southern hemisphere. So it's the southern hemisphere summer in this case, but you see that you've got this band of relatively high pressure along 30 degrees, right? That's your subtropical high. And it's a very regular band here, whereas in the northern hemisphere, it's a little bit more irregular here around 30 degrees. And you've also got this band of relatively, unbroken westerly winds here in the southern hemisphere circling the polar region near 60 degrees. And the deal here is just that you have a lot less landmass in the southern hemisphere. So the southern hemisphere has a lot fewer, landmass and mountains and things like that to break up the circulations. So the circulations tend to be much more regular in the southern hemisphere, Whereas in the northern hemisphere, you've got all this land-sea contrast, you've got the Rockies, you've got the Himalayas, you've got the mountains of Europe. So there's a lot more going on to give you things that are more irregular. This is what it looks like in our summer. Now in the summer, it's exactly the opposite, because in the summer, the land heats up. Again, the temperature changes much more over land than it does over water. So the land heats up in the summer, the water on average stays cooler, and so you tend to get this really warm air sitting over the continents, which tends to give you lower pressures. Because it's warm, it's less dense, it's going to give you lower pressures associated with that. It's actually this low pressure that tends to drive the monsoons. So you've got low pressure, for instance, sitting over southern Asia here, and that low pressure is going to draw air off of the Indian Ocean. And so as a result, you're going to end up getting circulations that draw warm, moist air off of the oceans over the land, and that's actually what's going to give you the Asian monsoon here. We have a similar kind of thing that sets up over North America that tends to draw air off of the water over the land, which tends to give you more precipitation during this part of the year as well in certain parts of North America. Now in southern hemisphere again, you see this very regular band of high pressure near 30 degrees. And then you've got the polar front down here near 60 degrees. It's again much more regular. Because there's not as much land mass to have the same kind of impact as it does in the northern hemisphere. Notice that they've drawn the intertropical convergence zone here as well. Oh, it's red line. So in the summer, the intertropical convergence zone moves northward into the northern hemisphere. You're going to have your rainy season in the summer here over Central America and over the northern hemisphere parts of Africa, and as well as over India and southern Asia. But back in the winter, it moved to the south. And so that's when you have your rainy season here in the southern hemisphere. Okay, so east-west jets, north-south circulation cells, semi-permanent high and low pressure systems, primarily associated with the land-sea contrast. Is that the whole story? Well, no, of course not, because we also have our day-to-day weather. So on any given day, we can have all kinds of things going on that don't really fit with those patterns. The basic idea is that those patterns are averages. So if you average over enough days, you start to see these patterns emerge. But on any given day, you can have all kinds of different kinds of weather going on. And typically, the signal associated with those weather systems will be bigger than the signal associated with the averages. So mostly on any given day, what you mostly are going to see are those individual weather systems. So this is an example showing a big old low pressure system sitting over the U.S. We're actually going to start talking about this stuff in the next couple of screencasts, so I'm not going to say too much more about it now. We're actually going to spend quite a bit of time talking about it. So to summarize, if we think about circulation starting with the really big stuff, working our way down to the smaller stuff. So on the really big end, the biggest, most prominent circulation is our east-west jet streams in the upper troposphere. So we have our jet streams in the upper troposphere. The next sort of biggest circulation, if not the next most intense, but the next biggest at least, is going to be our north-south circulation cells with their associated upward and downward motion and rainfall and the associated wind belts. And then we also have our semi-permanent high and low pressure systems associated with land-sea contrasts and to some extent with mountains, but largely with land-sea contrasts. Semi-permanent high and low pressure systems. And then finally we have our day-to-day weather that propagates through on any given day. Okay, and as I said, with the next screencast, we're going to start to get into more of this day-to-day weather stuff.